Welcome to my tutorial about the T flip-flop. So first, what is a T flip-flop? A T flip-flop is a flip-flop that toggles or holds the present state of the output. So this is our logic symbol for the T flip-flop. The T here stands for toggle, the Q stands for the output, the Q bar stands for the inverted output, and the CLK stands for the clock input. So as you can see, there is a small triangle there. It means that the T flip-flop is an edge triggering flip-flop. And edge triggering means that the flip-flop only responds to transitions of a clock pulse. So, for the positive edge triggering, the flip-flop only responds from a low to high transition of the clock pulse. And a negative pulse triggering flip-flop responds from a high to low transition of the clock pulse, and it is signified by a small circle on the clock input. So next is our logic diagram for the T flip-flop. So it is a simplified version of JK flip-flop, and it is obtained by connecting the same input T to both inputs of JK flip-flop. So as you can see here, both the inputs J and K are connected together to a single input toggle input. So next is the characteristics for the T flip-flop. So first is the truth table. The truth table describes the next state of the output depending on its inputs. So a 0 here means that there is no clock pulse transition, and a 1 here means that there is a clock pulse transition. So when there is no clock pulse transition, regardless of the toggle input, our output stays the same. So we will write that as a hold. So next, when there is a clock pulse transition, however, the toggle input is low or 0. So meaning the output will still be the same, and it will also be labeled as a hold. And lastly, when there is a clock pulse transition and the toggle input is also 1, then the output will be toggled. So for our output here, it will be inverted. It will be labeled as Q bar, and we will label it as a toggle. Okay, so the characteristic table describes how the flip-flop responds given a specific present state input, and a characteristic table depends on the truth table. So for our first combination here, when our present state input is 0 and toggle input is also 0, then the output stays the same. So it will also be 0. And when our present state output is 1 and the toggle input is 0, it will also stay the same. So our next state output is 1. So next, when our present state output is 0 and our toggle input is 1, then it will toggle. So our next state output will become from 0, it will be inverted to 1. And it also goes the same for our last combination here. So both of them are 1, so the output will be toggled, it will become 0. And next is the excitation table. So the excitation table shows what input is needed to obtain a certain sequence of the output. And the excitation table depends on the characteristic table. So first, when our previous state is 0 and our next state is also 0, there is no change. So therefore, our toggle input is low or 0 because there is no change. Next, when our previous state is 0 and next state is 1, then there is a change. So rechecking on the characteristic table, our toggle input should be a 1. So next, when our previous state is 1 and the next state is 0, there is also a change. So our toggle input should also be a 1. So rechecking on the characteristic table, okay, there. So our toggle input is 1. And lastly, our previous state is 1 and our next state is also 1. There is no change. So it is obvious that our toggle input is 0. So next is the alternate logic diagrams for the T flip-flop. So it should be noted that the T flip-flop can not only be created from a JK flip-flop but can also be created through a SR flip-flop or a D flip-flop. So first is for the T flip-flop from an SR flip-flop. So the output is fed back to the AND gate behind the R, and the inverted output is also fed back to an AND gate behind the S. So next is for the T flip-flop created from a D flip-flop. So we just added an XOR gate and we fed back the output to the XOR gate with the toggle input. So next is our simulation. So we will be using the electronics workbench to simulate our T flip-flop. So this T flip-flop is made from a JK master-slave flip-flop with two asynchronous active low inputs. So the preset here forcefully makes our output high, and the clear here forcefully makes our inverted output high. So let us start the simulation. So as you can see, our outputs are toggling continuously. So that is because our T flip-flop is still not initialized. So there are various techniques to initialize the flip-flops, but for now I am going to manually initialize our T flip-flop. So first, let us forcefully make one output to be high. So take for example our preset. So now our output is high, and next we will be going to toggle the output so that the T flip-flop will be initialized. So let us turn on the toggle and make a clock pulse signal and turn off the preset. And as you can see, we have toggled our output and our T flip-flop is initialized. So let us demonstrate the functions of the T flip-flop. So first is when the toggle input is low. So when the toggle input is low, then there must be no changes in our output. So since this T flip-flop is a master slave, this is a negative edge triggering flip-flop. So every time that the clock goes low, the T flip-flop responds to it. The T flip-flop operates. So let us try. Okay, when the clock goes low, so there are no changes in the output. So let us repeat this. So there are no changes in our output. So next, when our toggle input is a high or a 1, then every time the clock goes low, then our output will toggle. So let us try this. So clock input to high and then low. So our output toggled. So let us repeat this if it still works. So every time the clock goes low, it toggles. So this is the end of our tutorial. Thank you for watching.